Hello everyone, this is Mrs. Lim, your physics teacher, and in this video, we will be covering Chapter 9, Thermal Processes, Part 1. In this video, we'll be covering 9.1, what is thermal equilibrium, as well as how is energy being transferred by heating. But we'll only be covering one part of it, which is about conduction. For convection and radiation, we'll move on to Part 2 of the video. Okay, so why is it very important to learn about this chapter is because we know that not only Singapore, the world is actually facing global warming. And because the world is getting hotter and hotter, people starts to use more and more of the aircon. Okay, but this is not a solution because the increased usage of aircon will result in a vicious cycle that will worsen the problem of global warming. Okay, so we need to learn how is heat being transferred so that we can think of more innovative ways to effectively and efficiently cool down our hot weather and without an increase in the energy demand, okay, which will further contribute to more global warming. Okay, so without further ado, let's move on. So the first part, before we go on into thermal equilibrium, you need to understand that based on the previous chapter, we have studied that all particles are made up of all metals are made of tiny particles, which are in continuous random motion. So all of them are in motion. So all of them have kinetic energy within them. Okay, but they also have forces of attraction between them. And so these forces of attraction actually creates the internal potential store. Okay, when the particles are being heated, they gain kinetic energy. But when you reach the melting or boiling point, the particles no longer gain kinetic energy. The particles, on the other hand, they will move apart because they are going to change state during melting or boiling. They are going to become liquid or become gas. And in the process of changing state, my particles must move further apart. Okay, so in order to move further apart, there will be an increase in the potential energy to overcome the forces of attraction holding them together. So the total amount of energy that a substance has, we call it the internal energy of a substance, is made out of two things. It's made out of the internal potential energy, which is related to the forces of attraction, and the internal kinetic energy, which is related to the temperature. As the temperature increases, the internal kinetic energy of the particles also increase. Okay, so when two objects are of different temperature and they are put close to one another or in contact with one another, okay, energy will always flow from a region where there is a higher temperature or from the hotter objects to a region of a lower temperature, which is the cooler object. Okay, this process will continue until, okay, both sides or both regions have the same temperature. And we said that they are in a state of thermal equilibrium. Okay, you've learned before the word equilibrium means balance. Okay, for an object to be in equilibrium, the net force must be zero, the net moment must be zero. Okay, and for an object to be in thermal equilibrium, it means that the temperature on both sides must be the same. Otherwise, energy will always flow from higher temperature to lower temperature. Okay, so the one in the yellow box, you need to memorize. Thermal energy describes a state whereby two or more objects have the same temperature and there is no net transfer of energy between them. If the temperature is not the same, there will always be a net transfer of energy from a region of higher temperature to a region of lower temperature. Okay, so we look at the scenario over here. You have three persons over here. So the lady is having a hot tea. The pink guy over here is having a iced coffee. And then the orange guy over here is having a bottled water. Okay, so they were chatting and chit-chatting. And then after that, the lady was realized, oh, I was so busy talking that I forgot to drink my tea. It's no longer hot anymore. So the hot coffee has cooled down. Okay, on the other hand, the pink guy was thinking, oh, all the ice in my coffee has melted. Okay, my coffee is no longer that cold, it has become hotter. So one of it is the tea becomes cooler, one of it is the coffee becomes hotter. Okay, and then the other guy starts to think, but why is there no change to my bottled water? Okay, so what is exactly happening? Why is there cooling down, heating up, and no change, all at the same time happening. Okay, so we zoom into that. Okay, it can be explained by thermal equilibrium. So at the start, okay, the hot coffee is at higher temperature. The hot tea is at high temperature, while the cold coffee is at a lower temperature than the room temperature. All of them are at the room temperature, while the bottled water is at the same temperature as the room temperature. So heat will always, or energy will always flows from a region of high temperature to a region of lower temperature. So since the tea is hotter than the surrounding, energy will move out of the hot tea to the surrounding. Okay, so the hot tea cools down because it loses energy. On the other hand, the iced coffee, the initial temperature is lower than the surrounding. There is ice in it. Okay, so the iced coffee will not lose energy to the surrounding. It will gain energy from the surrounding until it becomes equals to the surrounding temperature. Okay, but the water, since it's already at the same temperature as the room temperature, there will be no change. We say that it's already in thermal equilibrium with the room temperature. So there's no net transfer of thermal energy. Okay, so we can take a look at this. I have a hot substance and I have a cold substance. My hot substance is represented by the red particles. You can see that when it's very hot, the particles have a lot of kinetic energy, and then the particles are moving faster and faster. While when it's cold, the particles doesn't have that much energy. They are moving very slowly, vibrating on their spots. If I were to put these two particles in contact with each other, thermal energy will start to flow. Okay, because there's a difference in temperature. The heat will start to flow from the region of high temperature, which is from the red color one to the blue color one. So the red color one, the temperature will drops from 100 degrees to drop down, and then the cold one, which is the blue particles, the temperature will start to increase from 0 to a particular temperature, and both will reach the same temperature, which we call it thermal equilibrium. Okay, I am going to show you what happens. Okay, so I'm going to stop sharing this, and then I am going to okay. So over here you will see this. Okay, so this is the hot one, this is the cold one. Okay, and then I'm going to start. No, sorry, wrong button. Okay, okay, I'm going to put them together. Okay, so you see the hot one will start to transfer the heat energy or thermal energy over to the bottom one. So the red and the blue will mix up to be purple. Okay, then the temperature will drops, okay, to about 50 degrees. Similarly, the cold one at 0 degrees will increase in temperature until it reaches the same temperature at 50 degrees Celsius. Okay, so this is what I mean by thermal equilibrium. Okay, let's go back. Okay, so similarly, like what is shown just now, I have an object at 100 degrees and another object B at 30 degrees. Okay, if I were to put them together, there will be a net flow of energy because the temperature is different. They are not in thermal equilibrium. So the energy will flow from a region of high temperature, which is the red object, object A, over to object B, which is of a lower temperature. And after some time, okay, eventually they will reach the same temperature. So A temperatures will drop to 65 and B temperature will increase up to 65. Okay, so we say that it is now in thermal equilibrium. Okay, so energy will always flows from a region of higher temperature to a region of lower temperature. And when there is no net flow of energy, is when there is no difference in the temperature. We say that it has reached thermal equilibrium. Okay, so summary, okay, is what I just mentioned. Energy transferred from region of higher to lower temperature until both regions have the same temperature and are said to be in thermal equilibrium. This is very important and is the basis of before you learn about conduction, convection, radiation. we must always determine where is the energy flowing first. Okay, so the definition of thermal equilibrium is a state where two or more objects have the same temperature and there is no net transfer of energy between them. Okay, so we move on to the next part. How is energy being transferred by heating? Okay, there are actually three processes. There is conduction, convection, and radiation. Okay, so these are the three main processes by which the energy moves from a region of high temperature to a region of lower temperature. Conduction, convection, radiation. Okay, so I'll move on into conduction. Okay, the definition of conduction is a process of energy transfer whereby the energy is transferred through the passing on of vibrational motion from one particles to another. Okay, so what do I mean by that? Okay, you can take a look at this diagram. So I have a heat source over here. Okay, so this is in a non-metal. So over this side, okay, the rod that is in contact with the heat source, okay, the part of the rod that is in contact with the heat source will start to gain kinetic energy and vibrate faster. Okay, so this side is hotter, this side is cooler. So the energy will flow from a region of high temperature, which is the heat source, to a region of lower temperature, which is on the other end of the rod. Okay, so how does the energy get transferred over from this heat source all the way to the other end of the rod? Is by conduction. Okay, because this rod is touching the heat source. In order for conduction to happen, there must be direct contact with the heat source. Okay, so energy is transferred, okay, to the particles that is nearest to the heat source. The particles over here will gain kinetic energy. They will vibrate faster. Imagine this is a solid rod, okay? The particles start to vibrate faster, and then they will collide with their less energetic neighbors and pass the energy over to their less energetic neighbors. Their less energetic neighbors will then start to gain kinetic energy and then vibrate faster and faster, and the energy gets passed on through vibration all the way until it reaches the other end of the rod, and all the particles starts to vibrate at the same rate. Okay, when they vibrate at the same rate, we say that they have the same kinetic energy and they have the same temperature. Okay, so you can take a look at this, my GIF over here. So you can see I heat these particles. This particles is in contact with the heat source. It will start to gain kinetic energy, vibrate faster, and then it will collide with the two neighboring one. And then the two neighboring one will also start to gain kinetic energy, vibrate faster, and then it will collide continuously until the next one. And eventually, the energy will be passed all over to the other end. Okay, so in words you need to mention, those in highlighted one are important. It must be seen in your answer key whenever the question asks you, how does the heat get transferred through conduction? Okay, so you must tell me particles at the heated end will gain kinetic energy, vibrate faster. Then I need to see the word it will collide or it will knock against their less energetic neighboring particles. I need to see the word less energetic neighboring particles. And then they transfer the energy over to them. And then the heat will be passed along the rod by vibrating particles. Just take note that the particles stay on the spot and vibrate. The particles do not take the heat energy and move to the other end. Okay, so there is no net movement of the particles. The particles just stay on the spot. It's the energy that gets transferred from particles to particles. It's not the particles that takes the heat and move. Moving on. Okay, so materials that allows the energy to transfer very quickly through them, okay, are called conductors, thermal conductors, while some of the materials it doesn't allow the energy to pass through them easily. Okay, it takes a long time before the energy gets transferred to the other end. So for such materials, they are called poor thermal conductors, or we call it the thermal insulators. So in general, solids are definitely better conductors than liquid and gas, and the best conductors will be metals. Okay, best thermal conductors. Why? Because in metals, okay, not only does the particles are very closely packed together, so the energy can be transferred from particles to particles faster. In metals, there is also what we call free electrons or delocalized electrons or mobile electrons. Okay, what happens when heated, these mobile electrons will also gain kinetic energy, but instead of waiting to be passed on by vibration to the neighboring less energetic particles, your free electrons can move. So what happens is they will gain the kinetic energy, they will be free to move, and then they will move over longer distance before they collide with their less energetic neighboring particles. So on top of the particles to particles vibration, there is also what we call the free electron diffusion, where the electrons take the energy and move. Okay, so metals are definitely better conductors, or we can so-called the best thermal conductors. Okay, on the other hand, conduction takes place very, very slowly in gas. Okay, it takes place much faster in solid than in gas. Okay, so air is a very poor conductor. Why? Because in gas, the particles are very, very far apart. It is very hard for the particles to transfer the energy over to the next particles, because you remember they must collide with their less energetic neighboring particles before they can transfer the energy over to them. But in gas, the particles are too far apart, okay, for this particles to particles energy transfer. Okay, so this diagram shows you about matter. So all these blue circles are actually electrons. So on top of the transfer of energy by vibration of particles to particles, okay, there is this free electrons. These free electrons will take the energy, they will move before they start colliding. Okay, they will move, so the energy gets transferred faster. Next. Okay, I will not show you this video. You may watch this video on your own about how conduction of heat takes place. We will go through a few examples of how conduction is being applied. Okay, so over here you have ice wrapped in metal gauze. The purpose of having it wrapped in metal gauze is to, or it can be any metal things, or you can tie the ice to a piece of metal or a piece of rock. Okay, the purpose of it is just to make the ice sink. Otherwise, if you put ice into a boiling tube, the ice will always float on top because ice is less dense than water. Okay, so I repeat, the wire gauze, metal gauze, or whatever thing is just to pull down the ice so that the ice sink. Okay, and then it was observed that if I were to put a Bunsen burner at the top part of the boiling tube, the water at the top boils. Okay, but the ice doesn't melt. Okay, what is happening here, over here, you must be able to understand that. So there is heat energy over here, thermal energy over here. So this region is hot, okay, and we know that based on thermal equilibrium, the thermal energy will always flow from a region of higher temperature to a region of lower temperature. So it's hot here and it's cold at the bottom with the ice over there. Okay, so the energy will be going to be transferred from the top of the boiling tube all the way down. Okay, we know that convection cannot take place because for convection to take place, hot liquid rises. So the hot water will tend to stay at the top rather than move down. Okay, so the only process by which the heat from the Bunsen burner can reach the ice is by conduction. Okay, so the hot water particles here will gain kinetic energy, move faster, and then they will collide with the less energetic neighboring particles and transfer the energy over by vibration of particles. Okay, but water, what can you infer about this is because the ice haven't melted, but the water already boiled, it shows that the energy or thermal energy doesn't flow through this water easily to reach the ice. So we can conclude that water is a very poor conductor of heat. Okay, water is a very poor conductor of heat. Okay, or very poor thermal conductor because the thermal energy from the Bunsen burner does not reach the ice fast enough to melt the ice, even when the water is boiling at the top. Okay, next example. I have a barrel with a fire on top of it. Okay, and then if I were to put a wire gauze, the wire gauze is made of metal. If I were to put a wire gauze above the Bunsen burner and then I lift up the wire gauze, okay, I will see that the fire is on the wire gauze for a short moment of time, okay? And the bottom part, there will be no flame. Okay, so what is happening over here is because, again, the wire gauze is a very good thermal conductor. It allows the thermal energy to pass through it very fast. So when there is a wire gauze, it carries the thermal energy away from the air over here. Air is a very poor conductor. It doesn't allow the heat to pass through it easily. Okay, so over here, the temperature is very low. Or the temperature gets carried away by this wire gauze for a short instant of time when you just leave it up. Because the wire gauze is such a good conductor, it will conduct the heat very fast to it. And then, so the temperature of this wire gauze will be very high. It will be high enough to sustain the fire or the flame on top of it. Okay, so next, I'm not going to play the video, but what happens for this video is you will see that there is two plates which looks exactly the same, but one of them is a thermal conductor and one of them is a thermal insulator. Okay, and then you observe that the ice melts on one of the plate, but it doesn't melt on the other plate. So what is happening and which plate is the thermal conductor? Okay, so over here, the plate that is a thermal conductor is actually the one with the melted ice. So what is happening is you need to first determine the direction of heat flow. So this is ice. So the energy is flowing from the surrounding to the ice. Okay, surrounding is hotter than the ice. So it's from surrounding to the ice. Because it's on a conductor, it allows the energy from the surrounding to pass through it very quickly to reach the ice, and therefore the ice is able to melt. On the other hand, the other plate over here is an insulator. It doesn't allow the energy from the surrounding to pass through it easily, and therefore the ice, okay, which is on top of it, touching it, will not feel the heat or will not feel the energy so fast, and therefore it melts slower. Okay, so next, we have another one. Okay, whereby I have this. Let me hide this. Okay, I have this video whereby I have a plastic bottle at one end and a metal can at the other end. And if I were to wrap a piece of paper over it then and put both of them onto a fire, you will realize that the plastic one will burn first compared to the metal. Again, it's because metal, okay, whenever we are comparing about materials, it's always about thermal conductors or thermal insulators. So metal is a very good thermal conductor. It will allow the heat to pass through very fast. So when you touch this end, you will get burned. Okay, that's why the person is holding on to the plastic side and not holding on to the metal side. Okay, so the heat passes through it very fast. It passes through it so fast that the temperature over here is not high enough to burn the paper. But on the other hand, plastic is a poor thermal conductor. It doesn't allow the heat to pass through it quickly. So the temperature remains at here, the heat remains at here, and therefore the temperature over here reaches a high enough ignition temperature and it causes the paper to be burned over this side. So we finish about conduction and I will stop here for this part of the video.